Yeah. Good evening. I'm going to be talking about optimal cooperative rendezvous using the AerialVehicles.jl model library. My name is Rajeev Voleti. I have a PhD in aerospace engineering from UTA, Texas, in the US. And I'm currently working with Julia Hub, working on Julia Sim. And yeah, so Yeah, I'll start off with a bit of a recap on my talk last year. So the quad model is derived using force balance on a rigid body, and the quadrotor is a differentially flat system with flat outputs as the position in space, x, y, z, and the heading psi. So we use the position, velocity, rotation matrix, and the angular velocity to describe the state of our quadrotor. So the dynamics are defined in MTK. It's very well documented. The quadrotor is very well documented in controls, and it serves as a platform for showcasing controls, estimation, and other applications. So we so to follow trajectories design, we use a nonlinear geometric controller. The idea behind this is similar to backstepping. So it involves designing desired dynamics for the quadrotor and then backtracking, accounting for the nonlinearities of the system to generate your control input. So the advantages of using the geometric controller is that it accounts for the nonlinearity of the system. So the state decays to the desired value of the output exponentially. And so it ensures sort of precise tracking, which is evident from the graphic, which is kind of hard to do with a linear PID. You would need a lot of tuning. So yeah. So the geometric controller allows us to perform acrobatic maneuvers like stabilizing a falling quad or having a quadrotor track a like really tight spiral. So just a quick summary. This is the overall structure of the trajectory optimizer with the quadrotor using a geometric controller, which has been already presented last year. So this is an example of a simulation of the geometric controller tracking 4 waypoints in 3D space. So now I want to focus on talking about the cooperative control aspect. So we look at a non-homogeneous system of vehicles. By this we mean that the dynamics of each of these vehicles are different from the other. We consider a quadrotor and 2 ground vehicles for same time or simultaneous rendezvous. So the ground vehicle controllers are custom receding horizon controllers that take into account cooperation. And each of the ground vehicles one of them is a Dubinskaya and the other is a differential drive. So while modeling for all of the vehicles is done in MTK, we use infinite opt, which is an interface in jumped, and IP opt to solve the ground vehicle problems, and then Julia Sim control using OSQP for the quadrotor. So the cooperation in this case is classified as objective-based consensus. So for further details on this approach, I would implore you to read the reference provided. Essentially, what this means is that the cooperation state that is shared is set by the leader or the objective, which in this case is the quad. We assume that it is physically possible for the ground vehicles to reach the rendezvous point. The only shared state among the agents is their time to go, or TGO. So the quadrotor shares its time to go every second for when it initiates the landing maneuver. So the ground vehicles use this to compute an optimal control for the arrival. So just a quick summary of this is what our optimal control problem kind of looks like. The solution is obtained using the maximum principle. For our application, we just assume that our cost minimizes the control energy for each of the ground vehicles. It can vary based on the dynamics and the nature of the problem. And it's represented by L. And here, the TF is set to the time to go off the quadrotor, which updates every 1 second once the landing mechanism is initiated. So the equivalent NLP to solve for the optimal control problem kind of looks like this. So it's well documented in literature. We leverage the structure of an nth degree collocating polynomial in states and control to sort of initially roll out and optimize the coefficients based on our cost. So in our framework, we compute the optimal controls and use a control trajectory for up to NC samples. and at the end of which a consensus is evaluated. And as shown in the figure, using the time to go, we estimate the number of time steps to consensus, which is NT. This interval is then split into NC. So each horizon now has a set of scale collocation points depending on the degree of the collocating polynomial. And so once a mechanism to find the solution of the NLP has been obtained, the framework of consensus and convergence is piecewise optimal. Although with the caveat that time to go consensus must occur first, which could be a problem if you're dealing with a network of vehicles on the ground. And so for our equivalent NLP that we have, assuring second order optimality in order to conform to the Bellman principle would imply sort of generation of Hessian of the order of the degree of the collocating polynomial times the number of discretization intervals by the number of states, and then raise an error flag if this is ever non-positive. So that's just a caveat when trying to set this up. And so yeah, in this simulation, we'll see the rendezvous of two ground vehicles with varying dynamics with a quadrotor, utilizing the quadrotor uses like the same polynomial trajectory optimization and the geometric controller, and the ground vehicles, after the third waypoint is hit, will start to initiate the rendezvous. So once that third waypoint is hit, they start to autonomously achieve rendezvous at that fixed or finite time. So the controllers that are designed for this are not necessarily MPC based. There is no fixed horizon. And there is also an element of cooperation that comes into the picture because at any point, this is just one of the scenarios, the quadrotor may change its descent. And so you don't necessarily have to tweak anything about the controllers to sort of still make the rendezvous happen. So yeah, so this is just a little showcase of the various tools that you can use to set such a simulation up.
Thank you very much for your nice presentation.
Yes.
One question, what is the purpose of the rendezvous?
It's you usually when you use a quadrotor in like a geometric controller, you're trying to sort of, you have like a disaster situation, or maybe you are trying to maneuver a quad in places where it's not really maneuverable. And so the purpose of the rendezvous is to autonomously recover the vehicle based on the resources that are available for you.
And why do you need more than one vehicle for that?
The quad may be large, which is the case for a lot of, or it's not just a quad, it can be a fixed wing vehicle. It's dynamics independent. So you can even have separate sort of a recovery of maybe two or more vehicles, or you have only one ground rover. It's immaterial. The framework would still work based on that situation.
Thank you.
Yeah.
If I got it well, the cost that you use is the integral of u square, right?
Yes, that is for the ground vehicle. But for the quad rotor, we minimize the snap because we don't necessarily want to damage the motors of the quad. So the quad has a separate cost from the ground vehicles.
Okay, thanks.
Yep, let's thank the speaker.
Yeah.
I think there's a poster session next. Just, a big thanks both to the speakers who were very on time, and also to everyone who attended the mini symposium. I think there's a break right now, and yep. see you around. Thanks.